Hello, everyone. Welcome to another episode of Q&A about history of science and technology. And I see a number of questions that have been saved up here. Uh, there's one from Golga. Who was the first person to discover history? Why do we start researching old scientists and their work? I think there have been different periods of sort of human existence where there has been more or less interest in history. Certainly in antiquity, there were people writing histories, like Herodotus, for example, who was kind of summarizing kind of things that had happened before. I guess that in antiquity, there were a bunch of situations in which people would make inscriptions where they would talk about the amazing works of, King Darius or the amazing works of Emperor so-and-so. And I suppose that that was some version of history. But I think the idea of kind of abstracted history, where you were talking about the flow of history rather than just the accomplishments of some particular leader or whatever, I mean, that certainly happened in the classical period with folks like Herodotus and oh gosh, the Roman in Roman times. Gosh, who's the person that begins with P? I'm forgetting the name. Who Shakespeare made lots of use of in writing his historical plays. But so definitely there was interest in history at that time. Now I think the question of whether, for example, archaeology, I don't think had really been seriously thought about at that time. People had a habit of, a city kind of was, had an earthquake and buildings collapsed. People would build the next layer on top, and that happened typically in cities in antiquity. I think the idea of saying there is an ancient thing and we're going to go and dig it up and preserve it, I don't think that was a thing until probably the 1700s. The yes, I'm being reminded of Thucydides and Plutarch. Yeah, Plutarch was the one for the who wrote a lot of lives of people, which Shakespeare made use of, I believe. But in any case, the idea that there would be kind of a artifacts from the past that were worth excavating, for example, I think that was a much later idea. I think that the notion that there had been a history and it was important certainly exists well in the ancient in historians of ancient times. It certainly the version of history that they were writing, I think, was intended to be sort of an accurate history. I mean, remember also people like Julius Caesar wrote a history of the Gallic Wars, for example, that one assumes was somewhat accurate, but I think it was also a marketing piece of the time. I don't know to what extent there were glosses put on things. I mean, certainly the thing often quoted to British school children of the Veni, Vidi, Vici, the Latin for I came, I saw, I conquered, that Caesar is said to said he said in connection with Britain, I doubt was ever actually said as such in some sense. But in any case, the I think that the idea that sort of history would be that things like archaeology were worth exploring, I think was a phenomenon of the 1700s, late 1700s probably. And I think that there were early efforts. I know, for example, the villa that is the place where these scrolls that got carbonized in the eruption of Mount Vesuvius, that villa is that is copied in the Getty Villa in California, is that was, I believe, one of the first places where archaeological excavation was done under the with civil engineering done by, I think, as I recall, some Swiss civil engineer, and sort of a non-trivial thing to, you dig down, you try and preserve the building that was there. I think they only dug one story down, even though it turns out the villa was a three-story villa, and I'm not sure the lower floors have even yet been excavated. But in any case, then folks like Napoleon got all excited about history, and I think particularly things like Egyptian history and sort of going and sort of, I suppose, basing oneself on sort of having been kind of connected to this august history of ancient Egypt and so on, and that was so that was sort of another step in the I would say the heroism of history being talked about. And then there were things like, the British Museum was created, I think, in the early 1800s as sort of a place to maintain artifacts from, in those days, the empire, so to speak. And so that was, again, something where there was increasing interest in history. Now, when it comes to history of science and technology, I think that's been a much more recent kind of pursuit. I mean, when I was a kid learning history in school, none of it was about science and technology. It had all been about essentially political and military history. This battle happened, this person took over, et cetera, et cetera, et cetera. That was essentially all of the history. And this is now in the 1960s in England, sort of there was a slow transition being made to things like, well, let's talk about what it was like to live in ancient Rome or to be around in London during the plagues and so on. So there was sort of more of a social twist to history. The question of, well, what technology was important in history, I don't think really came up. And certainly the connection of what science was being invented in those times was never mentioned. I mean, I know for myself personally, for various reasons of details of schools, maybe I sort of was exposed to the history of the 1600s in England, I think 3 separate times, and I was never interested in any of those cases. If somebody had told me that that was the time when kind of mathematical science had kind of emerged, I think I would have been a lot more interested, even as a kid, but that wasn't something that was mentioned. Now, I think in terms of kind of the sort of efforts to talk about history of science as a discipline, I'm trying to think when that really emerged. I mean, there were efforts, academic efforts, like the Dictionary of Scientific Biography, which is a quite impressive effort done by, as I recall, one of the founders of, was it Scribner's or some other New York publishing company? And that was done probably in the 40s and 50s. It's a many-volume work. It's really very good about biographical material about lots of scientists. I think the kind of the efforts to sort of explore the history of technology were quite thin. I mean, the other kind of piece of that were things like the London Science Museum, which I'm kind of guessing was first opened sometime in the early 20th century, but I'm not absolutely sure. Might be even slightly later than that. It certainly very much existed by the beginning of the 1960s, because the very young me visited there. And at the time, the London Science Museum, like the Deutsche Museum in Germany and so on, was definitely a museum about kind of the technological artifacts of history. It had the Stephenson rocket locomotive, and it had all sorts of other kind of features of sort of achievements in the history of technology, mostly in England there. I don't know, I mean, in the US, there are things like the Air and Space Museum. I don't know exactly when that dates from, but that was, again, something which was sort of collecting the artifacts from the history of technology in the US. I think the things like computer history that was just really not a thing until quite recently. I mean, the computer museum that started in Boston was sort of a mixture of sort of historical and sort of about current computers. That was around in the 1980s. Um, then the Computer History Museum is much more recent in Mountain View, California. There have been a whole bunch of private museums that have various bits and pieces of computer history. There's a museum at Bletchley Park in England, which I think is sort of just getting more and more developed, that has sort of some history of computing. But the question of sort of preserving the artifacts from computer history has not been a particularly well-developed one. I mean, for example, preserving early software and early computer documentation, there's rather little that's been done on that. So, for example, the bits that were the early programs that ran on this or that computer, there's a small community of people who are trying to collect those things, but it hasn't been a very organized effort. And unlike sort of books and things where at least there's probably many copies of that book and somebody will sort of keep the book and it might be in libraries and so on, there's no such similar organized repository that, I mean, there's some that are starting to exist, but there hasn't traditionally been. It's not like there've been sort of libraries of mainframe computer software that have sort of been in every town, and so somehow one version of that software will survive. No, to the contrary, it's once the mainframe is obsolete, it's decommissioned, and the software for it goes along with that. So I think it's something where that history has been complicated to preserve. Now, when it comes to scientific history, there are certainly archives of many scientists, typically at I don't know, national libraries or universities and so on, at some various kinds of institutions that have fairly long history. I think I've looked at many such archives. Most of what's in those archives is written documents. If there were sort of objects that had been kind of used, you know, I don't think those have mostly been archived. I mean, with specific scientists they have, but much of the time they have not. Now, so, and in terms of the kind of recreation of scientific history, some part of it has become easier because, well, there were things like once academic papers started to be a thing in the late 1600s, originally with the Royal Society and so on, people were sort of publishing the kind of the blow-by-blow updates of what they'd figured out. Now that convention changed because the early kind of scientific papers, academic papers, looked more like what we would think of as a blog post today. They were more sort of chatty descriptions of what was going on, rather than the more formalized kinds of things that you see in academic papers today. I suspect we've lost a ton of scientific history because certainly by the 20th century, the academic paper became this very formalized thing. And for example, it wasn't really a thing to talk about the things you tried that didn't work out. It was really just, here's what we figured out. This is the answer. You know, an example of this that I've been exposed to recently is trying to learn about the history of studying discrete models of space. That's something which people have wondered about since antiquity. You know, is space discrete or continuous? And end of the 19th century, it became clear that matter is discrete, molecules exist. The thing that I had not realized until very recently, even though I've been interested in this topic for a long time, is that in the beginning of the 20th century, sort of all of the standard greats of physics, Einstein, Bohr, Heisenberg, and so on, all believed that space would turn out to be discrete. They tried to make specific models. Those models didn't work out. By the 1930s, they'd sort of given up on those models, and kind of it became the accepted wisdom that space must be continuous. But I was kind of looking for sort of the evidence of what people had thought, and it's surprisingly hard to come by because it sort of didn't work out And so it never got written down. For example, for Einstein, there's a letter from 1916, for example, where he's saying, in the end, it will turn out that space is discrete, but we don't have the tools yet to understand that. In the case of Bohr, for example, my data is even much more bizarrely anecdotal. It's a friend of mine ran into Chandrasekhar, famous astronomer who spent much of his career at University of Chicago. But apparently, Chandrasekhar had in his wallet a card that he had got from Niels Bohr that contained a little formula that was a formula that was kind of in quantum mechanics terms, a commutation relation related to the discreteness of space. It turns out to be completely wrong, but apparently Chandrasekhar carried this around, so I'm told, that so that he could take it out and say, even a great scientist like Niels Bohr could write things which were complete nonsense. And his evidence for that was this kind of theory, which in detail was not correct, for the discreteness of space from Niels Bohr. So these are complicated threads to pull on to try and learn these aspects of history of science. And yes, the history of science is less well documented and told than typical political military type history. I suppose, as in many of these things, the history is probably somewhat, in the case of political and military history, that's always has to be understood through the lens of who is ever telling it, so to speak. I mean, it's always been interesting for me to realize that the thing that I learnt about as a kid in England that was called the American War of Independence is called the American Revolution in the US. I'd never heard the term American Revolution before I lived in the US. And people in the US will never have heard it called probably the American War of Independence. These are the same events told from a different point of view. I think that's probably happened less in scientific history, although there are things about scientific history that have been confusing. For example, in the history of mathematics, a chap called Eric Temple Bell wrote a bunch of kinds of biographical sketches of mathematicians, which are very lovely to read, and in many cases quite apocryphal, in the sense that they tell heroic stories, but those stories aren't necessarily well grounded in fact. And yet those stories have become kind of the, for some of those characters, have become oh, but that's how it was for many people. I mean, the same thing happens, for example, with movies about things like the movie about Alan Turing, the Imitation Game movie, which is historically very poor. I mean, the devices and set design is quite lovely, but the actual script in terms of and the presentation of Alan Turing and his personality and what he did is very wide of the mark. And yet, for many people, that's probably become the vision of Alan Turing, so to speak, from that. Well, let's see. That was a little bit of a story about let's see. Okay, there's a question here from Layla. How do you think about history when you find contradictions in research, such as two experiments running the same study yet providing wildly different answers? Which do researchers and scientists trust or believe more? What factors are involved in these decisions? Well, that's an interesting question. I think that there is a huge amount of sociology involved in these things. I mean, there are many. There sort of ends up being a certain weight of history that develops in some direction or another, and how that develops is really it's very similar, I think, to how beliefs develop about political things and so on. It's sometimes it's very clear what's right fairly quickly, and sometimes it's a long time before it's clear what's right, and sometimes a huge volume of kind of science gets done on the basis of something that isn't right. I mean, there are many examples of this. I mean, a good example which got very entrained with politics was the Lysenko versus Darwin story about evolution. The Lamarck rather. The So, the Darwinian idea that sort of the only thing that gets passed from one generation to the next is genetic information. The Lamarckian idea that during the life of an organism, things can happen to it that then get passed to the next generation. And that was, for example, in the Soviet Union, there was a big push along the lines of the Lamarckian interpretation. I'm not quite sure. I'm sure that had some relationship to the whole kind of Marxist doctrine. I'm not quite sure. I remember what the connection was between sort of the Darwinian, you're stuck with whatever genetics you have, and you can sort of change during your life. That undoubtedly has some political resonance, but I'm not sure I remember what that was. But in any case, that caused sort of a lot of work to be done in the Soviet Union, particularly on the basis of this theory of sort of this Lamarckian theory of evolution that was very different in other places. And so the weight of what seemed to be the right theory fell differently in one part of the world than in another. And I think of course, as is so often the case in science, and certainly in biology in particular, the Darwinian thing is mostly the right story, but there's a little bit of Lamarckianism that happens because, the egg cell does have other stuff than the DNA in it, getting passed from one generation to the next. So in a sense, there was sort of this after, Lysenko and the other Lamarckians were sort of discredited, and then the pendulum swung very strongly in favor. It's Darwin and nothing but. And that was from the early part of the 20th century in the West, for example. That was very much the story, and it also was, and so that became kind of this big belief system that was by the 1980s, people were talking a lot about sort of the relationship between sort of pure Darwinism and everything is the way it is because that is the way that would lead to the fittest organism, and natural selection was kind of the strongest force, versus kind of there were developmental constraints. So you just couldn't make an organism that would have wheels or something like this. And it was because of the mechanics of the development of the organism rather than because of the evolution towards greatest fitness. But that was quite sort of sociologically fraught discussion for quite a long time. I mean, that's sort of come to some kind of equilibrium now. That particular one, I think I talked about that another time. That particular one was made all the more complicated by the sort of the conflict between the idea of origin of species and the kind of biblical account of creation and so on, which had again sort of polarized people in those different directions. But there's to this whole point about different kinds of approaches to things. I'll give you another example. In particle physics, by the beginning of the 1960s, there was this whole question of, well, if one looked at smaller and smaller scales, would one find different constituents of matter, just like one had found, atoms and nuclei and protons and electrons and so on? Would one, inside those things, were there yet more fundamental elements or not? And there were two schools of thought. Kind of the school of thought that said, well, in the end, there'll be something underneath. That emerged in 1964 or so as quarks being the story of what was kind of underneath in things like protons. And the alternative was the so-called more democratic theory, where there was no kind of winning, I'm the most fundamental particle, but instead there was this whole sort of thing where every particle had other particles as constituents. There was this whole notion of sort of bootstrapping, where interactions between particles would lead to other particles, which would lead to other particles and so on. And there were sort of a whole democratic kind of congress of particles in some sense. Well, there was sort of that went back and forth for quite a while In fact, probably until the early 70s, that was going back and forth. Was it the S matrix theory that was all of that sort of ended up with this kind of democratic, all particles are equivalent type thing, or was it something where there were subconstituents in particles? And I guess that I got to witness the ending period of that interaction. Now, of course, in the irony of scientific history, the idea of the S matrix and the bootstrap and all this kind of thing, which was kind of killed by the mid 1970s by sort of the success of the quark approach to things, is back. It came back in part with string theory. It's come back in different ways now with conformal field theory and things like this. But these sort of old, well-developed ideas have a habit of never actually dying. They just come back in a somewhat different form. String theory itself was originally a theory that came out of this kind of early S-matrix 1960s type idea. It was sort of reinterpreted in terms of supergravity and so on in the 1980s, and sort of emerged in its more current form that way. So I think now that wasn't a case where there were different experiments. There have been plenty of cases where there are different sort of experimental results. Let me think of some examples. There were a bunch of detailed ones in particle physics, right? When I was getting involved in that field in the mid 1970s, there were all sorts of sort of anomalous results that have been seen in particle physics, and some turned out to be right, some turned out to be wrong. And kind of how did that develop? People did more experiments, and then things tended to clarify. I think that was the main thing that happened. And sometimes people would sort of pile on to the wrong theories and start making wrong experiments and start making theories about them. For example, that's happened. Oh, it's happened a bunch in cosmology. I think an interesting case in modern times is the dark energy idea, which one could alternatively talk about negative mass matter that has gravitational repulsion instead of gravitational attraction. Does that exist or not? It's a complicated thing to do all these cosmological experiments and observations, and it's sort of gone back and forth about how much of that is needed. Is the universe really expanding? Is it becoming sort of to the point where it will coast forever? Are these observations of distant and ancient galaxies, how should they be compared to modern ones and so on? And I think these are cases where sometimes there's a big piling on of theoretical work on top of something that might or might not be a correct experimental observation. I think the thing to realize is that both in the development of theory and the development of experiment, sort of the leading edge is always difficult. So, you have a theory, you might have a fundamental theory, as I think we have now for physics, but figuring out how to connect that fundamental theory to something you can do experiments on, there's a big, long road to get of figuring out lots of details to get to the point where you can compare with experiment. Then when you do the experiment, it's likely to be some very detailed property of something that requires, the biggest telescopes, the highest energy particle accelerators, and so on. You're right on the edge, and it's difficult to do the experiment. And there's a great tendency then for it to be a bit sociological, what happens, because people are like, you do the experiment, people really want to, given that somebody spent $1 billion or on an experiment, you kind of want something to work. And so there's a lot of psychological pressure for that. And sometimes people, and by the time you're bothering to do the experiment, you probably want it to work. You're probably not doing the experiment to prove that it doesn't work. Now, I'm remembering in the early 1980s, studies of proton decay. So there were a bunch of models, I even worked on some of them, which would predict that the proton should be unstable. It should decay with a lifetime of maybe 10 to the 30th years. And so then there would start to be these experiments of could you have this thing, you in order to observe proton decay, you really have to have this very stable environment, deep underground, a few miles down in some mine or something, shielded from cosmic rays as best you can do that. And then the question is, in this tank of liquid or something, every so often, does something just sort of blow up? Does one of the protons just sort of blow up and produce some high energy result that you could see with some kind of excitation, some kind of Cherenkov light or something like this, some evidence of a high energy particle there. Well, so that was an interesting case because people looked for it, and I don't recall anybody claiming that they'd observed proton decay, which is interesting because all the theories said it should be there, and I might have expected in the sociology of these things that somebody would start reporting it. Now, I mean, there were plenty of other funky things and experiments like that. There was the whole issue of solar neutrinos coming from the sun, detected in similar kinds of detectors. For a long time in the 1960s and 70s, nobody saw any neutrinos from the sun. And so the question was, why was that? Was the model of the sun wrong? Had the sun gone out? That was a possible theory. It takes a photon maybe 10 million years to kind of diffuse its way from the center of the sun to the outside. So a neutrino goes much faster. It doesn't get scattered as much. The sun is really not transparent to photons. So the photons are kind of getting stopped and so on many times on their way out from the center of the sun. But, people were wondering, has the sun gone out at the center? And there are no neutrinos coming from it because it's gone out. A kind of a radical possibility. But, then those experiments were eventually redone, and slowly it became clear that there were some things, I think, with the solar model that weren't very convincing. There were things to do with the way the detection was done, the energy of the neutrinos and so on. And eventually neutrinos were observed, although then there was sort of another thing thrown in, which was the oscillation from electron neutrinos to muon neutrinos associated with the fact that neutrinos, okay, so back originally, people thought neutrinos were zero mass particles traveling at the speed of light. But then there was sort of the possibility, well, maybe neutrinos aren't zero mass, but they have kind of a funny form of mass where the mass doesn't just kind of, mass in a sense is you can think of it in particle physics as being like every particle gets a mass by being sort of kicked every so often by a Higgs field that is sort of pervades the universe. It's a slightly hacky sounding theory, and I think the true story is probably a little bit different from that. But that's kind of in a first approximation, the amount the particle is kicked by the Higgs field determines the mass of the particle. And so, but normally it's like you kick it, but it's still the same particle. But in the case of neutrinos, the idea is you might be kicking it, and it might be, when you kick it, it might turn from being an electron neutrino to being a muon neutrino. And so it turns out that that is the case, it seems. And there is sort of, as neutrinos can come from the sun, for example, there can be an oscillation from one form of neutrino to another. But anyway, that was a tricky case where the experiments found something. There were various theories. Some of the theories were kind of outlandish. And it took probably 30, 40 years for that to kind of come to equilibrium. I mean, I would say that there are cases where people will report things which are really kind of strongly expected from theory, and then there's sort of a question of were the experiments correct. So I'll give you another example. In the 1970s, a chap called Joe Weber claimed to have observed gravitational waves. And it was sort of Einstein's theory of gravity from 1915, general relativity, had predicted gravitational waves. This particular chap claimed to have observed them. And one couldn't explain where they were coming from because they were much more intense than the obvious known sources of gravitational waves. But for a while, that was sort of believed that gravitational waves had been observed. And I think it sort of gradually decayed. And then gravitational waves were observed sort of for real in 2015. 2015, is that right? By LIGO and so on. But there was and at a much lower intensity, pretty much where it was expected from actual calculations that have been done. Another thing, so that was a case where people expected gravitational waves, an experiment came along, but the experiment had various aspects which weren't quite right. Another experiment from the 1970s, I guess, maybe beginning, no, 1970s, was magnetic monopole experiment where it was claimed, a chap at Stanford claimed to have observed a magnetic monopole. So normally, if you have an electron that has an electric charge, and you can have a dipole where you have sort of positive charge and negative charge, but you can separate the positive charges off, the negative charges off, and you can have an electric monopole, so to speak, as well. In the case of a magnetic field, you can have a bar magnet which has a north pole and a south pole, but if you saw the bar magnet in half, you don't just get a separated north pole. You just saw the magnet in half, you'll get two magnets that both have a north pole and a south pole. And so there's sort of been a question for a long time, could there exist magnetic monopoles, the magnetic analog of electric charges? And in fact, Paul Dirac, back in the 1930s, had shown that if there was even just one monopole in the universe, then there are certain consistency conditions that you would have that would force the quantization of charge. So it was kind of like a cool theoretical result. Well, a magnetic monopole was claimed to have been discovered. I think, I don't know, people kind of were like, yeah, maybe that's true, and that would be cool, and kind of follows the Dirac idea. And it sort of gradually decayed. There were other cases. I mean, I'm remembering examples like cold fusion, where there was very quickly a big backlash against those experiments, electrochemistry experiments done in the 1990s. And I don't know why there was such an immediate backlash, because the people who had done those experiments were fairly well-known people in the field. It wasn't as if it was coming from sort of outside the field. Maybe there were enough vested interests in the idea that one couldn't sort of have free fusion energy immediately, that there was sort of a tendency to push back. But the pushback was very hard in that case, and sort of these experiments are a fake type thing. Whether in the end it will turn out that there's an effect there or not, I think still remains to be seen. But there was such polarization that it became sort of a thing you couldn't study in that case. There are other cases. I'm reminded, we could tell the story of Arthur Eddington, and it was an interesting sort of theory experiment interaction. So when Einstein invented general relativity in 1915, one of the predictions was that light going past the sun should be bent twice as much as it would be in the Newtonian theory of gravity. And so the way you observe that is with a total solar eclipse, where you've kind of blotted out the main disk of the sun, but you can see a star, the light from a star, even close to the edge of the sun, and you can see as the star still in the same position that it would have been if the sun hadn't been there. So in 1916, there was a total solar eclipse, and some American physicists were off to go and figure out whether whether the Einstein effect was correct or not. The eclipse happened to be in Crimea, and it happened that they arrived in Crimea a couple of weeks after the US had entered World War I, and they were turned away you can't set up all this weird equipment here, we're at war type thing. And so it's interesting that they were turned away because the calculation that Einstein had done was wrong. I don't remember. I don't know actually what the actual result he had claimed was, but it wasn't correct. So then the 1919 comes around. World War I has ended. Arthur Eddington, the British physicist who was a sort of pacifist, conscientious objector in World War I. World War I ends, and in a sense, there was sort of a great kind of political statement of, I'm just going to go prove that the theory from this German scientist who was sort of on the other side in the war is correct, and sort of we're all scientists and friends now type thing. So Eddington went to South Africa to observe another total solar eclipse and reported, yes, Einstein was right. Fact is, it was probably fudged, or at least wishful thinking, because the data was sort of too good based on what was available at the time in terms of telescopes and so on. So that was a case where there was sort of some pressure to validate the theory. I think in now to be a little bit unkind to Arthur Eddington, later on he had a kind of a unified field theory, a fundamental theory of physics, and he had this whole mathematical calculation of how that would work. And among other things, he computed the fine structure constant, the electric strength of electromagnetism. And he computed that it was 1 over 136. It's a dimensionless quantity. And then, well, that was all good at the time because the experiments said that the value was about 1 over 136. But then the experiments changed. And the true number is around 1 over 137. And so Eddington famously said, and you add 1 for the trace of the matrix, which was just some, so the sort of the previous calculation was wrong, but now that the experiment changed, we noticed that the previous calculation was wrong. We added 1, sort of an unconvincing thing, chasing those kinds of directions. But, in the case of physics and so on, usually after an experiment is done a few times, things start to sort of shake out and you get to know what the answer really is. In the life sciences, and even worse in social sciences, experiments can be super hard to do. And there are, questions about, is it right, is it wrong? And people will have vastly different explanations of what's going on. I'll give you an example that comes to mind from economics. The efficient market hypothesis. The hypothesis is the correct theory for the value of a stock is the discounted future value of dividends from that stock. So in other words, if you want to know sort of what's the price of company X's stock today, you can compute it if you only knew the future dividends from that stock. Now you would think that with all the data and all the historical data and so on, that there would just be an answer. Is this hypothesis correct or not? But yet people still argue about it. Presumably it's not really correct, but it's still something where there's sort of even though it's a pretty cut and dried hypothesis, you can still have sort of a disagreement about whether it's correct. And I think that if you go to the history of medical research and so on, there have been sort of endless examples where the data has been, experiments have been done, people come to some conclusion, people are very averse usually to theory in biology, partly because there have been all these cases where people have been sort of led in this theoretical direction, and then it turned out to be wrong, and they were kind of, they sort of overdrove the experiments because they had a theory. I don't think that's always the wrong thing to do. And certainly my own experiences in physics and so on have been, if the theory is clean enough, then it often is more reliable than the experiments. I think maybe I've told this before, but an early experience that I had in physics back in 1970, I was computing some particular thing on the basis of QCD, theory of quarks and gluons, and I was pretty sure I got the right answer. But yet there was an experiment that said these particles that I said should get produced at some rate were produced at a rate, I don't know, 5 times less than they were known not produced, at least down to 5 times less than the rate at which I said they should be produced. And so, that was a case where it turned out that experiment was wrong. And I was kind of like, I didn't know what to think at the time, because one's always sort of taught in doing sort of empirical science and so on, that the experiments are where you are the things you trust. But in this case, the theory was so clean, so strong, and was getting sort of successfully applied in so many other cases that it seemed very hard to understand how that could be wrong. And it turned out in that case, the experiment was wrong. I would say that, Yes, I see a question here which may be related to this. Um, um, let's see, several questions here. From Justine. How do historians maintain accurate history and avoid misconceptions as it travels through channels and different adaptations like plays and movies? You know, my principle about doing history is you've got to look at the original documents. And that's really the only way you're going to be grounded in knowing anything about what really happened. Now, also, when you can, you should talk to the people who are involved, although that's a tricky business. It's actually, in my experience, more fraught with difficulty than looking at documents because people don't remember very well and they will fill in, they'll tell a story, but that story will fill in a lot of things that aren't really quite right. Or they'll outright lie to you. That happens with some considerable frequency because if you say, I'm going to write the history of the thing that you're involved with, there's a tendency to try and sort of get the history written the way they would like the history to be written, which isn't necessarily the way the chips actually fell. So I think in terms of, in terms of doing historical research, it's look at the original documents, talk to the people who are involved. Another thing about historical research is, in my experience, in the end, the story makes sense. And what I mean by that is sometimes when you first are looking at something, it's like, oh, somebody had this brilliant idea and just on, this date in this year, they just figured all this stuff out and it came from nowhere. Never is how it works. There's always a chain that goes back a decade or more of how they got to that way of thinking about the thing, or what kind of unexpected forces there were on them that led to that way of thinking and so on. I mean, I know one of the things that's sort of terrible about that kind of history, when I've done that kind of history for myself, and I'm like, well, I figured this interesting thing out back in 1980 something or other. And it's like, how did I come to figure that out? And I'm pretty good at keeping archives, so I usually have a lot of the documents. But in the end, there's usually sort of an arc of history that one eventually understands that says, well, the reason I was thinking about this is because I was thinking about this, this, and this, and I'd never put those things together. Even though I'd lived through it, I'd done those things, I didn't understand that the reason I started thinking about, I don't know, for example, making sort of computational models of things in nature was because I had been working on building a computer language, and that was sort of an experience of going from kind of primitives that you invent to kind of a structure that gets built up, rather than what one had more traditionally done in natural science, which is go from the way one sees things in nature to drill down to what's underneath that. And only decades later did I kind of realize the reason that I had this thought of sort of going upwards from simple models and seeing what their consequences were, rather than going downwards from seeing what actually happens in nature to how one might see what was underneath that, was because I had done this work on building a computer system, computer language, that was what led to that. It took real digging for me to extract that piece of history. Another one that I realized only very recently, a few months ago, was the relationship between the work that I did on sort of doing algebra by computer in the 1970s and beginning of the 1980s to the work that I did on studying, kind of doing computer simulations and studying how simple programs like cellular automata work. And I had realized that one of the things that happened in doing algebraic computation with a computer was that when I got algebraic formulas out, those formulas were kind of large-scale artifacts produced by computation. And by looking at them, one could get intuition. And that wasn't the typical experience of using computers. The typical experience was you've got just a few data points out or something like this, not a whole object, a whole structure you could look at and kind of get intuition from that structure. And I think realizing that was kind of obvious that was a thing you could do. And so when it came to visualizing things with a computer and learning from the sort of the object that came out from that visualization, that was sort of an obvious thing for me to do. And I didn't realize that I'd made those connections until a couple of months ago, 40 something years after that had happened. So it's always difficult to even for oneself, it's difficult to kind of draw the larger arc of history. But sometimes I'll think, well, this or that thing is how things happened, and I'll remember it roughly, and I've got detailed archives, and I'll go back and look, and I'll realize there was a ton of detail missing, or even sort of there was a very important element that I just completely forgot. But you can only find that by sort of going back to the original documents and looking at things. In terms of how kind of misconceptions develop in things like movies and so on, the truth of it is some stories are, if you want to tell a good story, it may not be the story that was a historical story. It may be a much better story if you juice it up in various ways than the true historical story, which was like, well, somebody was sitting around and thinking about this for a decade, and they led a kind of simple life for all that time, and they were gradually working on this stuff, and they wrote down one thing and then another thing and then another thing. That doesn't make for an exciting movie. And so I think that there's a sort of a different objective to make a good movie and to make an accurate sort of historical portrayal. And there's some things where it's kind of it's often the value of a movie existing at all probably greatly exceeds to people being interested in that history and so on, greatly exceeds. If the movie didn't exist at all, it's much worse than the movie exists, but it's not historically accurate, I think, in many cases. So, but on the other hand, the forces of what determines what's in the movie are not necessarily the forces of historical accuracy. Let's see. Paulos asks, how do scientists react when breaking news is discovered in relation to the history of science? Yeah, when things show up that one just had no idea were there, like the Antikythera device that was discovered around 1900, but it was only kind of interpreted slowly got more and more interpreted as an early mechanical computer. Sort of that was emerging in the 1960s and more seriously in the 1980s and so on. And yeah, that's like, well, we completely didn't understand the sort of state of technology in antiquity. I would say that is still viewed as a bit of a kind of a sideshow to other things, and it just doesn't fit in. One doesn't know how to build sort of a bigger historical story around that. I'm trying to think of other cases where there have been kind of perhaps even shocker sort of breaking news in the history of science. I mean, occasionally, there are works from antiquity which were thought to have all been lost, and then they're found, and that can change directions of things. I'm trying to think of cases where something that had been long believed. Usually, I think really people don't care enough about history of science that it's that much of a shock. I mean, yes, there are this thing wasn't really discovered by the person it was named after. Okay, that's par for the course, happens all the time. And people, will in modern times, there's sort of a tendency to add more names onto things to try and rectify that. But at some level, I don't think that creates a giant wave. I think occasionally there've been sort of so and so has been written out of history. Often the number one reason for that is because the thing they did, studying astronomical plates to find this or that thing, or doing something with, making cardboard models of a polyhedra or something, that those things were not things for which there is a mainstream way to record those things. The mainstream recording is some academic paper which has a very definite structure. Same thing has happened with people who develop tools. I mean, I would say that if you look at, even my own efforts probably in building mathematical models and language and things like this, those are not the effect of those efforts is not well recorded in sort of the academic literature, because those tools exist. Many people use them. Many people use them to do the research for academic papers, but it's not always the convention to say, and I use this tool. It's just, well, here's the result for my academic paper. So it's kind of invisible to history what actually happened there. And I think some of the kind of, oh my gosh, there was this whole group of people who did all this important stuff, and they've been sort of written out of the history. It's, well, it wasn't that they were written out of the history, it was just they were never written into the history, because the things they did were kind of supporting, tool building, whatever. And yes, they may have been the sort of the critical, they may have been at the moment of discovery. I mean, a famous example of this, 1968, the discovery of pulsars. There were a couple of physicists who built this whole radio astronomy observatory in Cambridge, and there was a young graduate student who was the person sort of on duty when the pulsar, when there was sort of the radio signal from the pulsars. Now, she could have goofed it completely and just said, oh, there must be an instrumental error, I'll switch the thing off. That would have been a big mistake. But there's been sort of a long running story. I don't know the full details of that particular story, of sort of how much was it the graduate student who happened to be on duty who was the key person, and how much of it was the kind of the multi-decade build out of the whole radio astronomy technology stack that should be considered the critical sort of piece of the discovery. It's a mixture, and it depends on what it depends on how you're thinking about that discovery, which piece you think is the more important piece. And both pieces had to be there. If either one of them hadn't, if somebody else had been on duty that day, watching the system, they might have done something, kind of silly, and they might have lost that data. But on the other hand, one couldn't have been there to see that signal if the whole thing hadn't already been built up in the past. And again, I think it's sort of an interesting thing that it's true in many fields that sort of the heroic contributor can shift around over time. I mean, one that I think is maybe it's not really a pet peeve of mine, it's just an observation that language design for computer languages and so on is a really, in many ways, a very pivotal activity. Yet is an activity that you don't hear much about. It's like you'll hear about so-and-so proved some great theorem, and you'll know, Andrew Wiles proved Fermat's last theorem. That's a super cool thing, and it has, it closed a multi-century chapter of mathematical history. But on the other hand, in terms of sort of the effect on things, there are things like, the design of some language, the building of some system or something. These are things which actually have a pretty big effect. But yet it just so happens that activity has never been sort of heroified, so to speak. I mean, the same thing has been true in other cases. It's like, when the first astronauts existed in the US, it wasn't clear whether they were going to be sort of heroified, or whether they were just going to be the people who were pushing the buttons like the poor monkey who'd been sent up before them, so to speak. And it just turned out that the way that evolved, they sort of became heroic. I think it's another interesting thing when you look at technology, there are sort of heroic contributors at some level to the technology that we all use all the time, and much of the time you won't know their names. For example, GPS. Do you know who created GPS? I think there was some couple of people. I don't know the history all that well, but most of these things, there was a person behind the creation of these systems, and in technology, it's often not known. I mean, there are cases like Thomas Edison, who became sort of very famous, and around that, and there are other cases where it is known, but often it isn't known, and it's sort of just a different thing from So it's complicated to and that's one form of kind of breaking news of didn't you know that so and so was responsible for this thing, and maybe the didn't you know is somebody one's never heard of but one should have heard of, and so on. But I think history of science, I'm not thinking of too many sort of shockers that have arisen in the history of science. I mean, the other kinds of things that you might consider shockers are things where it turns out that some particular piece of science was deeply enmeshed with some rather unsavory piece of history, and that certainly has come out a few times. And I suppose another thing that could come out is this or that, this or that experiment was fudged, but if it comes out at some point decades later and it turned out, well, it might have been fudged, but the overall result was correct, then it's still a meaningful thing. Let's see. Gosh. Elsie is asking, any perspectives on the historical development of our knowledge and understanding around memory, human memory, concepts like working memory, eidetic memory, insights from AI and machine learning and so on. I happen to have been thinking about some of these things recently, as it turns out. I've been trying to think about the question, which I thought was going to be very straightforward, but I thought I kind of had this one nailed, but I really don't, is if we had bigger brains, what kinds of things would we start to be able to do? Just like we have brains that are bigger than cats and dogs, and we can clearly do things that are different from what cats and dogs can do. But sort of what does that look like when we scale up? And so that's caused me to have a bit of a think about things like, well, about neuroscience and memory and so on. I mean, I think that the sort of the mechanics of human memory, I think it was sort of the thing that it's something to do with the neural net that's in our brains. That's been sort of a thing since the 1800s. How it works in detail, still very much up in the air today. The idea that it's something to do with synaptic strengths, well, it seems likely. And the fact that artificial neural nets, where that's the piece that's been captured, seem to do the things that are so close to the things that we manage to do as humans is sort of circumstantial evidence for that claim. But the idea that the possibility that there might be individual molecules whose pieces of RNA or something that encode at an atomic scale some memory, that's not a completely disproved theory yet. I don't think it will turn out to be the case, but I don't think that that's not really a disproved theory. Now, when it comes to these things like concepts like working memory and so on, and sort of what leads to that, one certainly imagines that working memory is some sort of recirculating data in the brain rather than something which has been sort of put into some more permanent form of, pores in a membrane or some other thing like that might just sort of sit there without active rejuvenation, so to speak. I think the history of psychology and studies of the mind and so on, I'm not sure I don't think that I have a well put together picture of how that really works. I mean, there are sort of philosophical ideas about the mind from whether it's Aristotle or Descartes, but they were very much, let's think about the mind in terms of our experience of the mind. And then there were much later sort of physiological kinds of things about let's dissect brains and kind of get an idea of how they work. And then in the 1800s, mid-1800s, between people like Helmholtz and people like William James, there was sort of the emergence of an experimental sort of approach to psychology and psychophysics and so on, where you could potentially measure, what was the, how much could humans distinguish this or that stimulus, things like this. And there was sort of a slow kind of merging of essentially the philosophical thinking about thinking and the more experimental, this is what a learning curve actually looks like. How many times do you have to do this before you know how to do it at such and such a level of effectiveness? And then into that whole thing was George Boole's efforts in the 1840s, introducing Boolean algebra that he originally thought of as kind of laws of thought, kind of going from what Aristotle had done with his kind of syllogistic logic of kind of logic encapsulated in particular sort of sentences that make logical sense, making it a more formal mathematical kind of thing. That didn't really merge with kind of thinking about the mind, I would say, until probably the 1940s and McCulloch and Pitts and neural nets and things like this, and maybe to some extent also things like Turing machines as emulations of kind of mind-like activity, computational activities. I think that would be a fair thing to say. I mean, I think that people like Gottlob Frege thinking about the foundations of math, I don't think they thought of that as a kind of mind-like discussion. They thought of that as more a discussion about the formal structure of mathematics and so on, not really a story about how human minds work. I think that was a thing, the fact that that sort of theory about kind of the idea that there could be a formal theory about the foundations of math and that might be connected to sort of mind-like things, the machinery of the mind, that was really, I would say, an Alan Turing kind of thing from 1936. I mean, Kurt Gödel in 1931 had some awareness of that, had some awareness of the fact that Gödel's theorem was sort of reflecting a bit on minds, although he kind of imagined that it was mostly saying minds can do stuff that these formal systems can't. And so I think that was sort of a late thing. And I think the concept that one could really sort of merge the idea of neural nets and sort of the computational experiments on neural nets and so on with kind of thinking about how brains work. Well, in the 1950s, automata theory was very much sort of entwined with cybernetics, which had been sort of an attempt to understand sort of control and so on in sort of both animals and machines. That had been sort of an idea from the 1940s to really think about, how you would make sort of both robotics and control of animals. And that kind of segued a bit into this automata theory that in the 1950s, and then the artificial intelligence term invented in 1956 in connection with a conference about automata theory. So there were, the idea that there were kind of biological alignments with sort of electronic devices was very much a thing. I mean, like John von Neumann was talking about organs as what we would now call gates in computer logic. So he had sort of a very biological metaphor for that. And I would say then computer technology took off and people kind of, the idea of sort of that computers were brain-like kind of fell away. I mean, back in the 1950s, people were talking about computers as giant electronic brains and so on. But pretty soon the sort of computer technology took off and people were not thinking about computers as particularly brain-like. And there was a small strand of artificial intelligence research where people sort of imagined, well, computers will somehow be able to do brain-like things. That was the common belief in the 1960s and so on. It turned out not to be as easy as people thought. But the connection, I'm trying to think, there were certainly groups like at MIT where there was a small distance between the people who were like cutting up frogs and so on and trying to observe signals in their brains and so on, and the people who were doing sort of the thinking about computers and AI. I would say that was a rare piece of contact, and I suppose that contact somewhat expanded by the beginning of the 1980s when computational neuroscience started to become popular, although it took a very long time, it was a long road to get to the point where sort of the computational approach to neuroscience is an accepted part of the general approach to neuroscience as a field of biomedicine, so to speak. And I think that's, I mean, that really has only been in the last, I don't know, 10 years or so that I would say that sort of that kind of merger has been fully ratified. So a few thoughts there. I think, yeah, let's see. LC asks, have you thought about applicability and leveraging of LLMs in historical deep dives with vast collections of original material going forward? Yes, I have thought about that. I think that's interesting. I mean, in other words, can you get sort of a whiff of some idea by having an LLM grind through 100,000 source documents? I think that's a quite plausibly a thing you can do. I mean, it sort of mirrors the fact that if it was numerical data, you would do sort of numerical data science on that data and say, oh yeah, there's an effect here. There's an anomaly here. LLMs can sort of do that kind of thing, but with text. And it is interesting. I mean, a project I've been, well, supposed to be hoping to do has to do with the history of neural nets and really trying to find the origin of some of those ideas that goes back into the 1800s. I think there's sort of a practicality of, are all those documents ground up into retrieval augmented generation sort of semantic databases or not? Are they used as training data for the LLMs and so on? I think there are some very practical kind of issues about that. But absent that, yes, it's a very reasonable thing to start asking sort of what are in this corpus of documents, what are kind of sort of vague indications of thinking about this or that thing. I think that's something LLMs might very well be able to pick up. I mean, it doesn't do you any good if the source documents just don't exist, or the source documents are handwritten things in some archive somewhere that that haven't been put into computerized form. But yes. Let's see. Well, I should probably wrap up a moment here, but let me see if there's just one more. Oh boy. All right, I'll try to do one more and then I got to go back to day job. From Sam, can you talk a bit about Planck and what led him to introduce Planck's constant? I actually learned something about this history that I haven't checked yet. I just learned it 2 days ago. So the story of Planck. Well, Max Planck was a pretty kind of, I would say, conservative thermodynamicist in Germany, late 1800s. And he had studied a lot of kind of every, aspects of thermodynamics and so on. The big thing, the big ticket thing to do in thermodynamics in the late 1800s was to prove the second law of thermodynamics, to prove the law of entropy increase. And, Kelvin had worked on that, and Boltzmann had worked extensively on that, and Clausius had worked on that, and Maxwell had worked on that, all kinds of people. I think finally we actually have a good answer to this, which I kind of have figured out over the last quite a few decades, and finally wrote a book about recently. But in any case, that's modern history. In the ancient history, sort of the big thing was prove the second law of thermodynamics. Why does entropy increase, etc.? Well, Planck, mostly a pretty conservative, dyed-in-the-wool kind of thermodynamicist, making measurements of things and so on. He had a theory. His theory was that radiation, that is electromagnetic radiation, and what was then known, it was known that there was radiative heat, that there was infrared radiation that could transfer heat as there was some kind of wave that could transfer heat, and it was an electromagnetic wave. And Planck had the bright idea, well, maybe this is where the second law of thermodynamics comes from. It's somehow related to radiant heat. And so he tried to establish that, and he made a model for how that radiant heat would interact with excitations of molecules and so on. And although he didn't he was still kind of waffling on the atomic theory of whether really matter was made of discrete atoms or not. That was still not a sort of established thing. But then he he was trying to understand the interaction between radiant heat and heat of materials, and he made a model for this. And he found that the experiments that had been done on black body radiation by Stefan and people, I think, didn't fit what his model said should be the way things work. Well, it turns out Ludwig Boltzmann, back in the 1870s, had, as an attempt to understand kind of the sort of the statistical mechanics, the kind of how different configurations of matter could work out if molecules existed, had made this kind of discrete model for both matter and, well, had made a discrete model for lumps of energy that might exist, discrete lumps of energy, discrete quantized lumps of energy that might exist. And it was that model had certain predictions, but Boltzmann said, but of course energy is not discrete. So we'll just assume, we'll just say we'll take a limit, and we'll just use this discreteness as a calculational device that's of no significance. Well, Planck then said, well, actually, if you take that seriously, then, and you say that energy is quantized, even radiant heat energy is quantized, and therefore electromagnetic energy is quantized, then you would get results which agreed much more with these curves. And he then fit those curves, and he introduced in this paper this thing he called H, which became known as Planck's constant. He even got the value fairly accurate based on the experimental observations that had been made. But he didn't really believe in sort of this atomic model. He certainly didn't believe in photons and things like this. And he kept on just sort of saying, well, this is a nice kind of mathematical construction. It was Einstein in 1905 who came along, particularly in interpreting the photoelectric effect, where you send an ultraviolet photon in and you get an electron out from a metal, that he had the idea of maybe the electromagnetic field is quantized, just like matter has turned out to be quantized. And then he connected that to what Planck had done, originally invented the terms like photon and so on. And it took Planck a decade to really sort of come to terms with the fact that, yes, what he'd shown was this discrete quantized thing. And later he really leaned into that idea, but it was a decade before he kind of threw off the prejudices of the much more kind of, let's go in this particular line, kind of traditional German physics direction. I think Gustav Kirchhoff was also a person involved in this whole thing. But the thing I learned a couple of days ago, which I haven't checked yet, so I don't guarantee this is correct information. But Planck's constant is 6.62559 times 10 to the minus 34 joule seconds. Am I right? I think that's right. In any case, that was what appeared in the formula that Planck wanted to use for black body radiation. But then when Einstein came along, he really wanted something which was about frequency, which dealt with angular frequency. So famous formula from the photoelectric effect, E equals H times nu, where E is the energy of the photon and H is Planck's constant and nu is the frequency. But one really wanted the angular frequency, that over 2 pi. And the claim, well, the thing that got introduced was H bar, H with the slash through it, which has often been called Dirac's constant. And I sort of had always assumed that Dirac had introduced it to make formulas a bit simpler, but apparently the claim that I was told is actually Einstein had introduced H bar. And the question is, where did he get the bar idea from? And the claim was that his wife at that time was a Serbian physicist. And it turns out in Serbian Cyrillic, there is an H bar character, which looks just like the H bar that we draw, that we write for what has become known sometimes as Dirac's constant. So I don't know what's correct in this history, but that was an interesting claim about sort of the origin of that particular notation. I don't know I don't know of other cases where people were putting sort of slashes through letters to represent things. So that has a certain plausibility from that direction. But anyway, that's just a little anecdote. But I think it is an interesting thing that Planck, in a sense, introduced the idea of quanta and so on against his wishes, so to speak, as a kind of a hack that leveraged what Boltzmann had done as a mathematical sort of device, and that this was done sort of in response to fitting a piece of experimental data. That just, well, this theory of Boltzmann's wasn't really intended to be a serious theory at this level, could fit this data, therefore this thing is in there. And then that, it really took, I would say, more Einstein's efforts to sort of turn this into, and this means something fundamental about the world. I think, in Einstein's case, I think one of the things that is notable about what Einstein ended up doing was his very sort of, in a sense, philosophical approach to physics, about thinking about sort of the big picture of how things have to work, and being also technically competent. But I think more important was kind of the big picture thing, which wasn't so much of a traditional thing in physics at that time. It was more like just do the measurements, work out the details, and so on. I mean, Boltzmann had also been more of a kind of a big picture thinker about physics, and really in his later years segued a lot into philosophy. And Einstein, I think, thought of himself as following on a lot from Boltzmann. Notably, Einstein in 1905, Einstein had these sort of big results on special relativity, the photoelectric effect, and Brownian motion. In 1904, he'd written a couple of papers about the second law of thermodynamics, which were also attempts to sort of apply philosophical thinking to the second law of thermodynamics. They didn't work. Those papers just weren't really right. But then he really hit the jackpot with these other cases where this kind of more philosophical approach to thinking about science really worked. And I think it's perhaps a lesson for progress in areas like physics that one can make now. I suppose I've been kind of perhaps on a leading edge of trying to think about things in a sort of big picture way, and then go and worry about the technical details and so on. But it seems that at least 120 years ago, that was a rather successful approach to doing physics that really advanced things a lot. And it's something, in the large institutional structure of science, it's something one doesn't get the opportunity to do all that often. I mean, in 1905, Einstein was working at the patent office in Bern, and which was sort of the equivalent of Silicon Valley in the kind of scientific technical world of its time, but was not kind of in the full establishment structure of science. And I think one gets a bit of advantage from that, as opposed to we're like Max Planck was, a very I'm a professor in a university, and particularly I think the German universities in those days were very, very scholarly, but also very kind of linear in the kinds of things that were being done. Boltzmann was in some ways an exception to that, who didn't always have a good time of it. But in any case, that's a few thoughts about the story of Planck. All right, time for me to go back to my day job, and I look forward to chatting with you all another time. Thanks for now, and bye for now.